Okay, welcome back. Now we come to an example illustrating the Otto cycle, and I've made this example very similar. The numbers are very similar to the example that I did yesterday about the Carnot cycle. And it says a polyatomic gas initially at a pressure of 650 kilopascals. So it's the same initial pressure that the gas started in yesterday's Carnot cycle problem. And the initial temperature is 340 Kelvin, has a volume of 0.008 cubic meters. So same state one, same gas, same everything. During the power stroke, it expands adiabatically to a volume of V2, which is 0.0114 cubic meter. I've chosen the same volume as the volume V, what we called V3 for the Carnot cycle problem. We call that the V3. This is we're calling the V2. It's the second state, right? So we call this state 2. State 2. Okay. Then the heat is expelled from the gas isovolumetrically as the exhaust valve is opened and the pressure drops to 280 kilopascals, state 3. So the stages of this problem are different because it's an Otto cycle. It's adiabatic, isovolumic, and then adiabatic and back to isovolumic. Okay. So then that one I'm calling state 3. And then here, during the compression stroke, it is compressed adiabatically to its original value, which is its original volume, state 4. Finally, it returns to its initial state isovolumetrically as the spark plugs ignite and add heat to the gas, and we close the circuit. Okay, we close the whole loop. Okay, so now let's write down all our given information. P1 is going to be equal to 650 kilopascal. V1 is going to be 0.008 cubic meter. T1 is equal to 340 Kelvin. Remember, we calculated the gamma of this gas, so I'm going to use the same value. It's a polyatomic gas. It's going to be, gamma is going to be 1.2857. 1.2857. And then the number of moles we also calculated. Okay, so since we're using the same gas, everything initially is the same. So let's write down also the other given pieces of information here. V2 is 0.0114. 0.0114 cubic meters, that's given. Okay, and then here the pressure of the third state, P3, is given. P3, 280 kilopascals. And what else is given? Well, that's it. Not much other information. Let's draw the PV diagram of this cycle, and then let's ask a bunch of questions based on it, right? So even though this problem starts out the story over on the top here, in the real engine, remember, for Otto cycle, it actually starts here. The gasoline comes in, then we compress it adiabatically, then we go up isovolumetrically, then we go down, then we go down, then we exhaust the gas, new gasoline comes in. Then you go like this, we go like this, okay? But it doesn't really matter for the sake of our problem. We can start out at this corner and still go down like this and still ask a bunch of questions based on that, even though in the real life it actually starts out here, goes this way, 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 and then these two stages going this way and then back, they cancel themselves out, so it doesn't affect the overall the working of the engine, right? In yesterday's problem, I had a similar situation, right? Where we started out here, right? And then we went isothermally to some other volume, we called that V2, and then we went adiabatically all the way to the same volume that I'm calling V2 now, right? Then we went isothermally back, okay? Then we ended up somewhere here, and then we went this way back to, so if we had to superimpose the Carnot cycle that we did yesterday, we would go down like this to some V2, then we would go down here, okay, then we would go back isothermally to V4, then we would go back adiabatically. So just from superimposing those two graphs, it looks like the area under our graph is more than that. But of course it depends on the 280 kilopascals. Maybe that's not way down. So it depends on what the number that the problem gave here. But it does look like this one is going to have a bigger area, which means the gas is going to do more work. So maybe it's going to be more efficient. We don't know exactly. Okay. So now let's erase this one. Okay. So now let's ask a bunch of questions on this. Okay. So what could be our questions? Well, the first thing we can say is what are the pressure, volume, and temperature in each state? So of course we want to calculate what? T2, what is T2, P2, right? And then over here, T3, we don't know, right? But the volume is the same. And then a P3 we already know. So what is calculate T3? And then also calculate T4. And then calculate P4. Okay? So as long as we have that, we've got all our information, right? And then we can say how much heat is extracted from the system between state 2 and 3. So then over here, it's dumping the heat out. This is Q cold. Okay? So that's the amount that you dump in. So calculate that, and then also calculate how much heat comes into the gas in this state, Q hot. Okay, so then this question is going to be B, what is Q cold and Q hot? Okay, after that we can say what is the work done by the gas in each stage? So W1, W2, W3, W4. Well, in an isovolumic process, no work is done by a gas, so that's easy. We can just do W1 and W3, right? So see what is W1, W3, right? And then W total, and then the efficiency of the engine. W1, W3, once we get W1 and W3, we can calculate W total and then the efficiency of this engine. And then E, what is the change in entropy? This first one is going to be adiabatic, right? In the adiabatic process, we know that we're going to have P1 V1 to the gamma is going to equal P2 V2 to the gamma, right? So let's calculate that. 0.008 divided by 0.0114 raised to the power 1.2857 multiplied by 650. Okay, that's going to be 412. So the pressure drops quite a bit. So P2, let's add the information here as we find them. P2 is going to be 412.24328. 24328 kilopascals. Okay. Kilopascals. Okay, now I'm going to erase the questions. Okay. And then start adding the information. So then what else do we need here? Well, we need the temperature T2, right? So how do we do that? We can say P2 V2 is equal to nRT2. So P2 we already know 412.24328 times 10 to the third. V2 we already have is 0.0114, and then the number of moles, which is going to be the 1.83956, 1.83956, and then the gas constant 8.314, and then we can solve for T2 that way. So we'll take the number that we just got, the kilopascals, then I'm going to multiply this by... So we noticed that the temperature drops quite a bit. In yesterday's experiment, the temperature didn't drop a lot. We did isothermal then adiabatic, right? Isothermal then adiabatic, and then we noticed that the temperature that we dropped was 320. The original temperature was 340 and then 320, and then the temperature difference between the hot and cold reservoir was very little, right? So since the temperature didn't drop, the temperature difference between the hot and cold is very little, the efficiency of the engine ends up being very inefficient. This one is probably going to be more efficient because the temperature difference is more. We got T1 is 340, T2 is 307. Then the temperature is going to even drop even more when we expel the heat out, right? So it's going to even drop one more step, okay? So then now let's calculate T3. We already know P3 is 280 kilopascals, and then we know V3 is the same as V2, right? So it's easy to calculate T3, find out T3. So then T3 is going to be T2, I can cross multiply. T3 goes over here, T2 goes over there, P3 over P2. Okay, so T3 is going to be, the T2 we take 307.28, and then P3 is going to be the one that was given in the problem, 280 kilopascals, right? So 280 kilopascal, and then divide that by the P2, which is the 412. 412.24328 kilopascal. Well, on this one, the kilo cancels the kilopascal, so we don't even need the kilo. You just do 307. All I needed from here. Then we go back to 4. T4 we don't know, P4 we don't know, but the volume we know is the same as the original, right? So V4 we already know is the 0.008. So then how do we calculate that? Well, we can use the relationship because we have two unknowns here, P4. So we can use the same relationship as an adiabatic process, right? We can say P4 V4 to the gamma is going to equal P3 V3 to the gamma, right? So the V4 is going to be the 0.008. The P4 is what we're solving for. So we can say P4 is equal to P3 V3 over V4 to the gamma, right? So it's the P4 we don't know. P3 we already know is 280 kilopascals. So then I can put here 280 kilopascal, and then V3 is going to be 0.0114, right? And then V4 is going to be the 0.008. 0.008 to the power gamma, which is at 1.2857. Okay, so let's erase this. So then now we know the P4. P4 is actually larger than P2, so it kind of looks like this. Okay, so this looks like this is P2 right here. Okay, this one looks like this, and it gets up higher. It gets up higher than P2, then it looks like that, something like that. So P4 is above the P2, okay? So this one, the one on the bottom is the P2, and then this one is the P4, okay? Then the next thing to do is calculate T4, the isovolumic process. That one is easier. I could say P4 over T4 is going to equal, and then over here is going to be P1 over T1, right? Because the last stage is isovolumic again, and then that relationship holds true for isovolumic. So what am I solving for? T4, right? So cross multiply, T4 is going to equal P4 over P1 times T1, right? So let's write that here. T4 is going to equal P4, right? Which is going to be the one that we just got, 441.48688, divided by P1, which is going to be the 650 kilopascals. So the kilo doesn't matter in that case. They're both kilo. Then I multiply that by T1, which is going to be 340 Kelvin. Okay? Okay, so now we've got all the data about all the temperatures and pressures at every corner, okay? The next question that we asked was, what was Q cold, right? And what was Q hot coming in, right? So then how do we get that now? The Q hot coming in, right? During an isovolumic process, what's the relationship, okay? Well, we've seen this before, right? Q is equal to delta E plus the work done by the gas. In an isovolumic, the work done by the gas is 0. So the Q is just equal to the change in internal energy, and then that depends if it's a diatomic gas, monatomic gas, or polyatomic gas, right? Triatomic gas. So then, in our case, since it was polyatomic, the Q into the gas is going to be 7/2 nR delta T. Okay? So then, if I want to find out the temperature, the QH, I just do 7/2 N is the 1.83956. R is the 8.314, right? And then I do the difference in temperature between here and here, right? So the temperature on the top is 340 Kelvin. And then I subtract from that the temperature over here, T4, which came out to be 230.9316. Okay? Cold. Okay, Q cold. So then you just use 7/2 1.8, 8.3, and then you just take the difference in temperatures of these two, right? T3 minus T2. So of course it's going to be negative, but usually when we write down Q cold, we just write down its absolute value, even though we know that it's negative. So we write down its absolute value, right? So we're just going to subtract the temperature T2, which is 307.28, minus the colder temperature T3, which is 208.7078, right? Okay, so then what's the work done by the gas? Well, the gas doesn't do any work in these two isovolumic processes, so it only does the work in the adiabatic, right? So how do we do that? Well, similar to what I did yesterday when I did the Carnot cycle, right? I'm going to do work is equal to constant, right, times integral dV over V to the gamma, right? And then the constant is going to be the P1 V1 to the gamma, so this is W1, P1 V1 to the gamma. And then when you integrate this, you're going to get V to the minus gamma plus 1 over minus gamma plus 1. And then you're going to integrate from V1 to V2. Okay, so then we're gonna P1, you're gonna put 650 times 10 to the third, right? And then the V1 is gonna be 0.008, right? Times to the power gamma, which is gonna be 1.2857, okay? And then, of course, on the bottom, you're going to have 1 minus gamma, so 1 minus 1.2857. And then you're going to have 1 over, and then you invert this, it becomes it becomes gamma minus 1, right? Gamma minus 1, so V2 is going to be 0.0114 to the power 1.2857 minus 1 minus 1 over 0.008, okay, and then it's going to be to the power 1.2857 minus 1, so it's just basically the 0.2857, okay, and then like I did yesterday, this is 1 minus 1.2857, it's going to be negative 0.2857, right, negative 0.2857, and then this negative is going to cancel the order of the signs here. You're going to take this and then subtract this from there. Okay? So then how do we do the work in stage 3, W3? So then I can use P3 V3 to the gamma, because that's what stays constant, right? P3 V3 to the gamma. P3 V3 to the gamma, and then I can integrate from V2 to V4, or V3 is the same as V2, so V3 to V4. So it'll be V3 to V4. Okay? So what will be different here? So here I'm going to put, instead of 650, I'm going to put P3, which is 280. So change this to 280. Okay? And then here I'm going to put V3, which is the same as V2, which is 0.0114. 0.0114. And then here I'm going to go V3 to V4. So over here is going to be V4, which is the same as 0.008, which is actually this thing, 0.008, right? And then over here I'm going to put V3, which is the same as V2, so it's basically this thing, 1.0114. So notice on this one, it's a little bit easier than the Carnot cycle. You're not really changing the volumes a lot. So this integral doesn't really change a lot. It just turns into a negative. That's it. Just becomes a negative. This part stays the same. This part stays the same. But instead of 650 and 0.008, you just have 280 and 0.0114. So I can just get the work in an easier way, right? I can say the work in stage 3 is just do more like a ratio thing. I can say the work in stage 3 is going to equal whatever the work in stage 1 was, right? Which is the 1751.58, right? But it's I'm gonna divide out, because remember when we calculated the work in stage 1, we had 650 here. So I'm gonna divide here by 650, but instead now I'm gonna multiply by 280, right? And then over here, it used to have 0.008 to the power 1.2857. So I'm gonna divide by 0.008 to the power 1.2857. Then I'm going to multiply by 0.0114 to the power 1.2857. Okay? So you see what, I'm just doing it as a ratio. So then I can take this 1751, put it in here, multiply it by 280, divide by 650, and then over here I can take the ratio of the volume before and then raise it to the power 1.284. So I'll just do it that way and I'll get the answer quicker. But then I know that the work is negative because I am going backwards, right? So I'm just going to do this part first. Then I can calculate the ideal maximum efficiency of this engine. Okay? Okay, efficiency of the engine, 100% times the work that the gas does divided by QH. Okay, the work that the gas did was going to be what? The difference of the two, right? 1751, 561.89. Divide that by QH, which is going to be the 5,838.3613. So you're dividing it by how much heat we had to come into the system when the spark plugs fired, right? So then you're dividing this by this. So 560 is going to be quite a bit more efficient than the Carnot engine one from yesterday's problem because it looked bigger, but the looks is kind of deceiving. It depends on a lot of factors. The Carnot engine was, I believe, 5.5% efficient. This is about double that, something like double, but not that much more efficient. So 9.62% efficient, okay? The efficiency of the Otto cycle can be written like this: 100% times 1 minus 1 over V2 over V1 to the power gamma minus 1. This ratio V2 to V1 is called the compression ratio of the engine. The compression ratio R. Okay, so notice that for the Otto cycle, the efficiency primarily depends on the ratio of the V2 to the V1. If I make the compression ratio larger, that means I expand the gas more. The ratio of V2 to V1 is going to get larger. When this number gets larger, then you're going to have 1 over a larger number, which is going to be smaller, and efficiency is going to approach closer to 100, right? If V2 is the same as V1, right, then that means the compression ratio would be equal to 1. Well, 1 over 1 would be just 1. 1 minus 1 would be 0, right? So you don't want to have a compression ratio of 1. You want to have engines that have compression ratios of 4, 5, 6, 7. Okay, bigger it is, the more efficient it is. For Carnot cycle, the efficiency depends on the ratio of the two temperatures. So we have T hot minus T cold over T hot. Okay? For Carnot cycle, the Carnot efficiency is the difference in the two temperatures between the hot reservoir and the cold reservoir. the bigger I make the difference, the better that is. But here, the bigger I make the difference between the two volumes, the more efficient it gets, right? For the Carnot cycle, we can say, because you can never have a 100% efficient engine, this proves that you can never have a chamber that is 0 degree Kelvin, 0 Kelvin, right? You can never achieve 0 Kelvin, because if you could, then the T hot would be the same as the T hot. You could have a 100% efficient engine. So the second law of thermodynamics that says you can't have a 100% efficient engine is also saying you can never have a chamber that's 0 Kelvin. Okay. Okay. Now let's see if this equation is working. So we're going to have efficiency 100%, 1 minus 1 over V2 is the 0.0114 divided by 0.008. And then I'm going to raise it to the power 1.2857 minus 1, so that's going to be 0.2857. Okay, so what is my compression ratio in this example? Notice it gave me the same answer as when I took the work and I divided it by QH, right? They agree. So now you can see that for Otto cycle, this is the alternative way of finding the efficiency. And then for the Carnot cycle, it's T hot minus T cold over T hot. The next thing to do is to ask what is the change in entropy in each stage. Okay. So the change in entropy from state 1 to state 2. Right? Well, the first stage is adiabatic. In an adiabatic process, the change in entropy is 0. Okay, so that one is good, 0. Then we are isovolumically compressing the gas, delta S 2 to 3. In isovolumic, what's going to happen? You're going to do, remember, delta S is equal to delta Q over T, but then the heat into the gas is going to be what? dQ. It's going to be equal to the work done by the gas plus the change in internal energy of the gas, right? But the isovolumic process, the work done by the gas is 0, right? So this is 0. So then the delta E is just going to be the change in internal energy, which is equal to, since this is a polyatomic gas, it's going to be 7/2 nR delta T over T. Then I take the integral delta T over T, so then I get ln of T final over T initial. So in an isovolumic process, this is the general result. 7/2 the number of moles times R times ln of the final temperature over the initial temperature. So when I'm going this way, I'm cooling it, the entropy of the gas is going to decrease, right? So let's see what's going to happen. Delta S 2 to 3 is going to be 7/2 N is going to be 1.83956. R is going to be the 8.314. ln T final minus T initial. So T final is going to be T3, and then T initial is going to be T2. So T3 is going to be 208.7078 over, and then T2 is going to be 307.28. Okay, so then the change in entropy from 3 to 4 is going to be 0 since it's adiabatic, and then from 4 back to 1, right? So then I can just change this slightly, 4 to 1. So then it's going to be the temperature of the first stage, which is 340. So we have 340 on the top, and then the temperature T4, which is going to be 230. 230.9316. Right, so then I take the 340 divided by 230. That means everything we've done up till now is correct. We've proven that the change in entropy of a complete cycle is 0. Right? So this one, no change in entropy. This one, negative entropy. This one, 0. This one, you gain entropy, positive 20.706. Of course, we're assuming that we're doing this cycle quasi-statically, reversibly, so that by the time we come back to the origin, the gas is completely in the same state. In the real world, that never really quite happens. The gas is not exactly in the same state that it was when it first began. But this is a quasi-static, reversible process where the change in entropy of the complete process should be zero, and the gas is found in the same exact state at the end as it was in the beginning, right? So 20.706, negative 20.706, they cancel, and the change in entropy is zero. The last question was, if we run this Otto cycle backwards, right? We go down and we go this way, we go this way, we go this way. What would be the coefficient of power, right? Right? So the QH would be how much heat we would, how much heat, basically if we run it backwards, this one will go this way, right? And then the QH would go this way, right? So then QH would be a measure of how many joules of heat we would dump to the room. Imagine this is your room, right? And so we divide how much heat we dump into the room divided by how much work it took us to perform that task, right? So QH is going to be the 5838.3613 divided by the total work that is required to perform that job, right? So 58. If you think about it, that's actually just an exact inverse of the efficiency of an engine. Instead of work over 5838, it's just exact opposite. So you could just take the efficiency of the engine, which was 9.62%, 1 divided by 0.0962, and then you would get 10.39, okay? So just forget the percentage portion of the efficiency, just express it as a decimal, and then invert the efficiency of the heat engine, and then you get the COP of the heating mode, okay? If it functions as a refrigerator, so then we would just do, instead of Q hot, we would do Q cold, 5276.5064 over 561.89. Now if I've done it correctly, I should get 9.39, one value less than the COP heating mode, right? Not bad, right? So now we have the foolproof that the COP refrigerator always one less than COP the heating pump, okay? So now you can see a good problem. This is the Otto cycle. You can see the differences between this and the Carnot cycle, and you have a good example of all the possible questions that can be asked about this kind of situation, okay? Thank you very much.